All right, guys, welcome to section 3.3. We are going to be looking at derivatives of trig functions. Okay, so we get to brush up on all of our trig identities and properties of our trig functions. And while we're reminding ourselves of all of our trigonometry, we're also going to be looking at how we're going to take our calculus approach to trig, and we're going to be looking at the derivatives of trig functions first. So we're going to start with the sine function. Okay, so what we're going to do is we're going to examine the graph of the sine function, because remember, the derivative, it has a very visual approach. It's the rate of change, right? It's how quickly a graph is changing. So let's start there, and then we'll look at our algebraic approach to finding the derivative. Okay, so we know that sines range from -1 to 1. And they're cyclic, right? They have a period of 2 pi. And we have these markers along the way. It's kind of like the x and the y points on the unit circle. Remember, for our unit circle, the sine is the y coordinate. Right, and it goes on forever in both directions. Okay, so at angle 0, right, the y coordinate right there is 0. So I'll just do it right there. And then as we go around our unit circle at pi over 2, 90 degrees, our y coordinate is 1. Then we keep going. At pi, our y coordinate is 0. Keep going around our circle. 3 pi over 2 is right over here. Now our y coordinate is -1. And then back around to 2 pi, and our y coordinate again is 0. All right, and then we are allowed to go otherwise. Remember, negative angles, we're just going counterclockwise. So negative pi over 2 is going to take us to -1. All right. So that's a review. And remember, it doesn't stop there. It just keeps going. And it goes on forever in both directions. So it's periodic. It's a periodic function. So let's examine this in terms of rates of change. Okay, so let's talk about the tangent lines along our sine curve. So first of all, we know that when we're sketching the graph of the derivative, we can focus on where the directions change or where our tangent line is horizontal. And when we're talking about the derivative, that's going to be our zeros. That will be our zeros. So let's start with the derivative because we're already talking about the zeros. Okay, so we're graphing the derivative of our sine function down here. And we have all these zeros. So it looks like we're going to, on the derivative, we'll have a 0 at pi over 2. So let me write all of our same axes. Okay. So we're going to have a 0 there on our derivative. We'll have a 0 here. And we'll have a 0 at 3 pi over 2. Okay, excellent. So let's see what else we know. We have periods of increasing. So between -pi over 2 and pi over 2, the sine is increasing. Our sine function's increasing. All right, and then, of course, that repeats in a similar pattern. And then we have chunks of intervals where we're decreasing, okay? And we know that when our graph is increasing, so like the yellow areas, that means that our tangent line is going to be increasing as well. So the slope of the tangent line is increasing. And since the derivative is rates of change or slope, it means our derivative is also going to be positive. So in this yellow area right here, our derivative graph down below is going to be positive. So maybe something like that. Okay, remember it starts off slow because the tangent line, the slope isn't as steep. Then right here is the peak of the steepness. And then our tangent line gets less and less steep until we get back to the 0. All right, and then same thing kind of right here, but we don't complete it. All right, and then as far as the blue parts where our graph is decreasing, if we were to draw a tangent line at any of those points, our tangent line would be decreasing as well. So the slope of all the tangent lines is less than 0, excuse me. So that means the derivative, which is, symbolizes the slope or the rate of change, will also be negative. Okay, so from pi over 2 to 3 pi over 2, our derivative function is going to be negative. Okay, maybe something like that. And then over on this side, something like that. Okay, so take a look at that graph. So again, we had that our function is sine of x, and we're trying to find the derivative down here. And this is our sketch. Does it remind you of anything? Let's see, it's periodic function. Whoops, this should be 2 pi. Sorry about that. Does that shape remind you of anything? Kind of looks like cosine, right? So let's examine that. So that's kind of our hypothesis right now. Based on the graph, the derivative of sine kind of looks like the cosine. So it actually is, but we're going to show it using our algebra skills and then everything we've learned about derivatives. So we're going to show that the derivative of the sine function is cosine of x. Okay, and how are we going to do that? Well, we're going to go back to our limit definition. Okay, so we're going to have to show that this expression right here, when we plug it into our sine function, it's going to equal cosine. So that's our job right now. All right, so let's hop to it. So f of x is sine. So we'll plug in x plus h into sine. And f of x just sine of x, okay? And now notice if we were to plug in the 0 right now, that would be, that would go to 0. So sine x minus sine x is 0 over 0, okay? So we're going to have to rearrange some things. So common mistake, let's do a little side note. Remember that as far as sine is similar to logarithms, where if we have something in the argument right here, we're not allowed to distribute the sine function. So that's a common mistake, is to just thinking we can distribute the sine function into our argument. And remember, the argument is protected by parentheses. Just like logarithms, the only way we can touch the argument is by using properties. All right, and we actually have a property. Here, I'll write it in green because green means go. We actually have a property for addition and subtraction of arguments in sine and cosine. So go all the way back to your algebra class. If we're looking at sine of x plus h, this is equal to sine x, cosine h plus cosine x sine h. Okay, so it's not as simple as just distributing that sign. So let's make that substitution, and we'll see what we can do with our expression. Because again, we're going to have to simplify it so we can get rid of that h. So again, it's going to be sine x cosine h plus, now the opposite, cosine x sine h. All right, and then we'll write everything else. All right, so what can we do? Well, we're going to just do a little bit of manipulation. So what I'm going to do is I'm going to put the sine x over here because I notice there's another sine x term, so maybe I can factor that out. And then I'm going to separate our fractions because we have terms and addition and subtraction in the numerator, so we can separate out each term by dividing it by h. So we're looking at this. So I'm doing a rearrangement and separating out our fractions. So we're looking at sine x cosine h. And then I am rearranging. And then I'm going to put that over its own h. And then I'm going to add the remaining fraction. Okay, and you can put this in parentheses, just so we're really clear on what we're taking the limit of. All right, so we know with limits, we have a couple properties with limits. When we're taking the sum in a limit, remember we're allowed to distribute our limit to each term. So we're going to do that. In addition, we're taking the limit as h approaches 0. So that means anything that just has an x in it, so sine of x, cosine of x, that's not going to be affected as h goes to 0. So if a limit as h is going to 0, sine of x or cosine of x is behaving as a constant, and we can move it outside the limit. So it's going to look like this, all right? So sine of x, we can factor that out and move the sine x to the front. All right, and now it's the limit as h approaches 0. So remember, I factored this out. I took it out. So cosine h minus 1 on the top. And then here, again, I'm going to distribute the limit sign, and cosine x is behaving as a constant since it's not dependent on h. So I'm going to move it out, and then what is that? Sine of h over h. All right, there you go. So what can we do now? Well, notice if we were to plug in the 0, unfortunately, we haven't canceled anything. So we're still going to get a 0 over 0, right? Because cosine 0 is 1. 1 minus 1 is 0. Over 0 is, whoops, there we go. Sorry about that, guys. Over 0, the denominator is 0. And likewise over here, this is going to be 0 over 0. So quick note, remember in chapter 2, we proved this limit graphically. All right, and we saw that as h approaches 0, this limit is going to approach 1. Okay, so that was a chapter 2 proof. So I'm just going to write 1 right there. We proved that in chapter 2 via graph. Numerical experimentation, really. There's also a geometric proof as well. If you guys are interested, it's on page 191. So it's optional. Okay, and then over yonder, what we have here, sine of x is still hanging out, and we don't know what this one is yet. So I'll just put a box there for now. And then we have this, okay? So far it's sine of x times something plus cosine x times 1. So we're going to focus on this one, okay? So tally-ho, let's focus, and we're going to try to figure out, I'll put this in a square too, we're going to try to figure out what that is. And then we'll know what the derivative of the sine function is. All right, so 0 over 0. What we're going to do here, and this is just something that, it's a trick, it's a tool, I should rather say it's a tool that we're going to use, and it's a technique that we can use for the remainder of the course. We can't do much as far as trig properties go with cosine x minus 1, but if cosine was squared, then we can start using the Pythagorean theorem, okay? So how we're going to square that cosine, we're going to be tricky and we're going to multiply it by the conjugate. And I keep saying tricky, but it's a tool. I like thinking of it as a tool. All right, so then a minus ba plus b is a squared minus b squared. Okay? And the reason why I like to do this, let's do a little side note, is once it's squared, we can use the Pythagorean theorem. Okay, so that's the Pythagorean theorem. We can do lots of things with this, right? We can divide each term by sine squared to get the cotangent squared plus 1 is equal to cosecant squared. We can divide everything by sine squared, to get, oh, that's what I just said. If we divide everything by cosine, then it's 1 plus tangent squared is equal to secant squared, stuff like that. But what we're going to do with this is I'm going to rearrange it to look like that. So we can subtract 1, and then we would have to subtract sine squared to get it by itself. So we're going to make that substitution. Cosine squared x minus 1 is negative sine squared x. So cosine squared is negative sine squared. Okay? All right, so that's our substitution. All right. Okay, so we still have a 0 over 0 situation, right? So this is what we're going to do. We're going to separate your sine squared into 2 copies of sine. Since, here I'll write it a little more scratch work, this is like sine x times sine x. Okay, that's what sine squared is. So let's rewrite it like this. So negative sine of h, and I'm going to put 1 copy with this h, and I'm going to put 1 copy of the sine with cosine h plus 1. All right? So now, where are we at? Well, we know what the limit, here let's separate these out to make it look a little nicer. All right, so we'll clean it up before we start talking theory. Let's move the negative on the outside, because that's like a constant, it's like negative 1, move it on the outside, and we'll distribute the limit 1, 2. Okay, so this we know, right? We know that this is equal to 1. So negative 1. And now this, we can actually plug in the 0 finally, because this is why we couldn't plug in the 0. This was making our denominator 0. But we just got rid of that. We said it was 1. And now let's plug in the 0 here, because now it's part of the domain. So sine of 0 over cosine of 0 plus 1. All right, sine of 0 is 0. Cosine of 0 is 1. All right, so what's 0 divided by 2? 0. And what's negative 1 times 0? 0. All right, so we were doing, that was our pit stop. So we just discovered that this whole thing in blue is equal to 0. Okay, so this is the derivative of the sine function, right? That's where we're coming from. So now we just said this was 0, so that's going to make this whole term 0. All right, and so all that's left is your cosine. So that's exactly what our graph was showing us, and now we are able to prove it precisely. So we have that the derivative of our sine function is equal to cosine. All right, and then we can do that exact same thing. So I'm going to number these because these are actually properties you're going to memorize. We can do that exact same argument, but with cosine. All right, and we can prove it in a similar manner. And we would get that the derivative of the cosine is negative sine of x. All right, we also discovered, and this is something to memorize, that the limit as theta goes to 0 of sine theta over theta is equal to 1. And then the other thing we discovered is the limit as theta goes to 0 of cosine theta minus 1 over theta is equal to 0. Okay, and then that's what we're memorizing so far. From these two derivatives, we can actually prove any of the other trig functions. And I might actually look or ask that question on an exam. So let me write that out. So we should know how to prove the derivative, or to show, right? When we prove, we show it using the definition of derivative. So know how to prove the derivative of your other tangent functions. So tan theta, cosecant, secant, or cotangent. And the reason why is because all of these can be written as some kind of quotient using sine and cosine. And we know how to find the derivative of quotients. So know how to prove the derivative of these. I'm sorry, I originally said using the definition of derivative, but we would be using reciprocals or ratios and the product and the quotient rule. Okay, so let's practice that. Let's find, stop it. We're going to show the derivative of the tangent is equal to, and I'll write all of these out later because you have to memorize all of them. But for now, let's just focus on the proof of the secant squared. All right, so how we're going to show this is by using ratios and the quotient rule. So the tangent is equal to y over x, or sine x over cosine x. Okay, so if we wanted to take the derivative of this quotient, what we do is we take the bottom function times the derivative of the top minus the top function times the derivative of the bottom, and then we divide it by the bottom squared. Okay? All right. So we just learned this derivative And we just learned this derivative. So let's make those substitutions. Do you remember what the derivative of sine was? Cosine. All right, multiplied by the derivative of cosine. The derivative of cosine is negative sine. And we're going to divide that by cosine squared. All right, so let's clean this up. Cosine times cosine is cosine squared. All right, and then this is the product. So minus minus becomes plus, and sine times sine is sine squared. All right, and in comes Pythagoras. Cosine squared plus sine squared is 1. All right, and we're almost done. 1 over cosine squared of x, well, that's the reciprocal of, or cosine is the reciprocal of secant squared. So there you go, that's what we were trying to show. Do a little box with a filled in. All right, so that's how we can prove any of our trig functions, finding the derivative of those just using ratios and the quotient rule. So now I want you guys to show the following. And you guys are going to show this is negative cosecant of x times cotangent of x. All right, so go ahead and push pause, and then we'll see how you guys do. Okay, so hopefully your first step was rewriting the cosecant as a reciprocal of 1 over sine of x. Cosecant's reciprocal is sine. Okay, and now we see we have our quotient. So taking the derivative of a quotient, its bottom function times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay, well, what's the derivative of a constant? It's just 0. So that first term is just going to go away. Sine times 0 is 0. And what's the derivative of sine? It's cosine. All right, and then so 0 minus 1 times cosine, or negative cosine, right? So negative 1 times cosine of x over sine squared x. Okay, and now at this point it's always helpful to look back and see where we're trying to go. And I have just, one expression here, but look at our answer, we have 2. We have a cosecant times a cotangent. So that's telling me I might have to separate this fraction a little bit. And I'm looking at the denominator, and there's 2 sets of signs here, right? So just how fractions work, here's that negative sign. I'm going to separate our fraction like this. I'm going to separate up that sign in the denominator. And now I kind of have something that looks like our answer we're trying to get to. We have 1, 2 terms. Now we have 1, 2 terms. And then what's 1 over sine x? That's the cosecant. And what's cosine over sine? That's your cotangent. That's exactly what you guys are trying to prove. Okay, excellent. So we have 4 of the trig functions and their derivatives, but we have 6 trig functions altogether. So feel free to try to prove those other 2, but for now, let's start memorizing all 6 of them. So I'll write them all in one spot. So first of all, the derivative of sine is cosine. The derivative of cosine is negative sine. the derivative of tangent is secant squared the derivative of cosecant, all right, it's the reciprocal of sine, so I'm kind of organizing them a little bit. By reciprocal is negative cosecant times cotangent. The derivative of secant is positive secant x tangent x, so kind of similar to 4, just a little bit. And then finally, the derivative of cotangent of x is equal to negative cosecant squared x. Okay, so there you go. So your guys are going to memorize these 6 functions. Let's try one more together using the product rule, and then we'll move on to limits. So we're going to incorporate this with the product rule, and the instructions could be something like, differentiate, find y prime, find dy dx, something like that. Find the derivative. And then the function is secant theta times tangent theta. Okay, so we see we have a product. That could be like our f function, and that could be our g function. Okay, so how does the product rule work? Well, first we can take our first function times the derivative of the second plus our second function times the derivative of the first. That's our product rule. And now, once we do our product rule, normally you do the product rule or the quotient rule first, and then we go through and take the derivative when the product rule or quotient rule tells us to. So, for instance, we know that the derivative of tangent is secant squared theta. And we know that the derivative of secant theta is secant theta tangent theta. All right. And now it's time to clean up everything. Let's see, that's 3 copies of secant right here. So this is going to be secant cubed theta. And then here we have, let's see, 1, 2. We're not going to distribute. We only distribute if it's a sum. This is just a product, right? So we can rearrange the factors. 2 factors of tangent and then 1 factor of secant. So we can do secant theta tangent squared theta. Something like that. Okay, and then just so you guys know, this answer is acceptable. But you're going to see when you see solutions to some of the homework problems, sometimes people do a lot of crazy things with this after they do this. For instance, I've seen things where they'll want everything in terms of secant. So they're going to write tangent in terms of secant. All right. Whoops. And just remember, here we'll do a little side work. We have this over here. We know cosine squared plus sine squared is 1. But then we can go through and we can divide everything by cosine. So we have 1 plus tangent squared, just cleaning up everything, is equal to secant squared. Okay, so tangent squared theta, subtracting 1 from both sides, is also secant squared minus 1. So if we wanted to get everything in terms of secant, and sometimes your textbook does this, we can make that substitution. And now that this is a difference, now we actually do distribute your secant, because it's not a product, it's a difference. And that was supposed to be a 3. Okay, so now what we have is we have 1 copy of secant cube, 2 copies, and we're adding them. So 1 plus 1 is 2. You add the coefficients. All right, and then you can get, something like this. That's fine too. Okay, so again, there's different ways to simplify, different ways to simplify, and you're going to see that in your homework examples.